Some of the most widely applied statistical solutions to solving batch effect problems are based on a relatively old technique called factor analysis. So we're going to explain factor analysis briefly. We're going to use an example related to the first application of factor analysis over 100 years ago, and it's related to the correlation in grades that students would obtain in class. So this table I'm showing you here is from simulated data, where I have simulated the test scores for several students across 6 subjects. So you can compute the correlation between, say, math and science class because you have several values for several students. And we can see that the correlation is relatively high. In this case, it's 0.67. Now, instead of showing you these numbers, I'll show you a plot of the numbers, which looks, it's a little bit easier to interpret. So we have here the 6 subjects, math, science, computer science, and then 3 others, English, history, and classics. The first thing we see is that the data is not independent. Independent data would look like the figure on the right, where you would have mostly white here in this picture as shown below. Red is a high correlation, white is no correlation, and blue would be a negative correlation. So if the test scores across subjects were completely uncorrelated, the picture would look like the picture on the right. And that would mean that if you're good at math, it doesn't mean anything on how well you're going to do in science or CS. But what we see here instead is that everything is correlated. If you're above average in math, you're going to be above average in all other subjects. But we see more structure than that. We also see that there's higher correlation between the STEM fields and higher correlation between the humanities fields. So even though everything's correlated, there's even more correlation between these two. So if we can model this using a factor model. So what we do is we hypothesize there are 2 hidden factors. W1 and W2 is what I'm calling them here. And that the observed data, which is the test scores, is represented here with y, ij. So this is for student I on subject j. And this is going to be a sum of linear combinations of these 2 factors. So the idea here is that W1 relates to your overall ability of getting good scores. And then your second W, your second factor, relates to are you stronger in humanities or are you stronger in STEM. So when we interpret these parameters alpha, so notice that every student gets an alpha for the overall W and an alpha for the difference between the humanities and STEM. That's how we would interpret these alpha. If you have a high alpha 1, it means you're overall a student who gets good test scores. If you have a high alpha 2, it means you are better at STEM than in the humanities. If you get a negative alpha, it means the opposite. So now we apply this model. If we were going to try to estimate what these W's are from the data. So now what we're going to go back and assume that we don't know anything. We just get this data set and we look at the correlation matrix and we infer that there's 2 hidden factors here. We don't know what they are, and we're going to let the data tell us what these W's are. And one way you can do this, it turns out, one of the ways you can estimate these W's once we pose this model is by using the singular value decomposition. And we're going to assume there's just 2 factors, so we just take the first 2 columns of V, and that gives us an estimate of the W's. And what we can see, if we actually look at them, we look at what these W's are and we look at them across the subjects, we see that the first one appears to relate to the overall. It automatically finds that your overall ability, it's positive, it's a positive constant for every single subject. And the second column of V appears to be related to the difference between the humanities and STEM. So it actually finds this automatically. This is the power of factor analysis, that you let the data pick what the what these W's are. So if we fit this model, we can estimate these W's, fit the model, and we explain about 78% of the variance, which is pretty high. Now, There's a more general way of doing this. We don't have to have just 2 W's. We can have many W's. And we can estimate them with PCA, or singular value decomposition. So this is what we're going to do when we have batches that we don't know what they are. We could, for example, model them with these factor models and try to estimate the dump weight. Now, to see how complicated these structures need to be in a real data set, let's look at this correlation matrix for the data set that we have been studying with the 8,000 and plus genes and 200 plus samples, where we have different ethnic groups that were recorded at different times. That's what this figure is showing us. And we can see the data is clearly not independent. There's structure there. You see these red squares and bigger red squares and smaller red squares. This is because there's correlation between samples that are probably driven by date, but it's much more complicated than year to year. So we could use factor analysis to try to describe this structure, and we definitely need more than 2. So that is something that we're going to try to do using R. We're going to try to find how many factors we need here to describe this correlation.